Hi, I'm Kyle. I'm a research associate on the TruSDEd project, which is basically aiming to bring cheap, in situ, and attestable network traffic processing to Internet of Things and sensor networks. This is joint work between myself, our other research associate, Chris Williamson, and our PIs, Professors Doug Paul and TruSDEd. So when it comes to actually defending IoT and sensor networks, we want to be able to inspect the traffic coming in and out of them in a fast, cheap, and secure way. And achieving all three goals at once is really quite difficult when you think about it. Like, security in this sense is primarily processing individual packets and trying to look for patterns in the traffic we're monitoring, for instance. So firewalls, deep packet inspection, access control lists, etc., etc. Nowadays we can do this in software quite effectively. Ideally though, we want to do as much of this processing in situ as we can. So if we can do this in the same location as our sensor networks, we're able to, say, monitor adverse behavior from one or more flows and act upon it in a far faster way than if we were, say, spending additional bandwidth or latency in steering all of our traffic towards some scrubbing service in a data center hundreds of miles away. And of course, when we think about sensor networks and network functions together, there's initially maybe some trepidation here. Like, when we think of network functions, we tend to think of like bespoke, expensive middle boxes that require a lot of space and power. But in contrast, sensor networks have such low data rates in the order of like tens to hundreds of kilobits per second that small single-board compute devices like the Raspberry Pi shown on the right here end up being potentially very good choices for doing this sort of traffic analysis on site, aware of space and power constraints. But this has its own set of interesting and tricky challenges. The first of which is that the sort of best-of-breed frameworks for doing this processing take up a lot of power and CPU cycles. Typically, to do this well, you either cut out as much of the kernel as you can, or you interface directly with the hardware. And as it turns out, interfacing directly with the hardware involves spinning CPU cores constantly, which is very wasteful when we consider the resource and power constraints we actually have to deal with out in the field. Meanwhile, when it comes to doing this securely, the state of the art now relies upon using very much server-only capabilities like trusted execution environments, which let you do interesting and powerful things like attest that the right code is running in the right place and nothing can interfere with it. But these are being stripped away from just about every class of hardware, which isn't, say, Intel Xeons, for instance. And of course, if we're dealing with small single-board compute devices, we don't really get to use the interesting and fun offload technologies like FPGAs or SmartNICs to actually make this work any faster. Just to add insult to injury, the devices themselves are physically vulnerable, as is memory stored in their non-error correcting RAM, including cryptographic keys and the like. So how do we reconcile these difficulties with cheap and portable single-board compute devices? Our methodology tackles this from two aspects. The first of which is the packet processing stack. So here we go for a two-tier approach, where we start with, say, functions encoded as individual Rust trays, as well as some specification of how to put them all together. And we compile these into both native code and eBPF binaries. These are then fed into our critical and high performance needing functions are fed into an XTP fastpath. So this is basically a region of the kernel where these special programs are all checked and verified, and they can run very quickly with low latency that is very well supported. In the event of more complex functions, we can simply push them further up the stack using, again, other kernel bypass methods, and ideally we only ever pay these costs for, say, 1% of traffic, for instance. The other problem we have to tackle is how to actually attest that this configuration is correct from both senses, in the sense of, have we received the right information from the server, and is the client who it really says it is the edge device doing the traffic processing. For this, we are using an interest in PUF devices, physical unclonable functions, which give a signature out for any input which relies upon some unclonable part of a circuit, for instance. Basically, this lets us authenticate keys keys and identities in the wild without root certificates and gives a strong attestation of physical devices. So main takeaways: cheap, low latency, and secure. We're working on user-RAN functions just now, state management and characterizing the PUF devices themselves. Thanks.